and welcome to this first lecture, substantive lecture on data generating processes and thinking about statistical models. So after this lecture, there's a rather long, detailed discussion of regression and reviewing regression related concepts. And most of the lectures in this class are going to be more like that. So this is sort of a one-off where I want to start by just thinking about what statistical models are, this concept of data generating process, and what I think is the most difficult thing about statistical modeling, which is coming up with a conceptualization of the world that we can then operationalize in some form of a statistical model using data that we've collected that has been generated through some process that we think relates to said question that we're interested in. So that was a lot of information packed into one thing. So let's start by just the most general statement, which is all statistical models are wrong. All statistical models are wrong. However, some are useful, and we're going to try and get a sort of a general idea of how we can get our statistical models to be useful. So what's the purpose of a statistical model? Well, the most obvious point is to take a lot of data, a big matrix of variables and observations, and condense them into a few parameters so that we can make sense of them. Now, that's part of reasons why it's always wrong, is because we're taking a lot of information, condensing it into less information, and by obvious virtue of that process, we're leaving out a lot of information. Now, we're going to store that information in some static process, usually error variance or some variance parameter, where we're going to hold that information and try to figure out stuff about it. But we are losing information, and that's the point. We can't, if we were interested in just understanding what everyone was like at every point in time, then we wouldn't use statistical models, but then we wouldn't get anything done because we'd be overwhelmed. So we want our parameters to be parsimonious, we want them to make theoretical, conceptual sense, and we want them to be able to represent this thing called the data generating process. So we want to condense all of our multitude of points into a very refined, small, conceptually coherent thing that is in some way related to how we got the data, and the data should reflect that in some way, and then we extract from the data these parsimonious parameters, and that's sort of the general frame of what we do. The models that we use have several purposes. So we use them for predicting. We want to forecast things. We might want to say who will develop some course of a disease or who will develop some outcome that we're interested in. We're interested in exploring associations, so summarizing relationships between one or more variables. What's the association between ethnicity and being stopped by the police, for example? We might want to extrapolate from a sample to a larger population. So we might have information on a particular school, and we want to say, can we then take this information about this school and apply it to all the schools in the state? And sort of the goose that lays the golden egg is causal inference. That's what a lot of us really want. We want to understand whether some change in policy, child welfare policies, affect out-of-home placements or something like that, right? So we want to know if I do this thing that we're going to call X, will it have an outcome on this thing that I call Y? And causal inference is a really tough thing. We're not going to be spending a whole bunch of time talking about the details of that. That's a whole course in and of itself. But suffice it to say, that is going to be the specter that looms over almost all of the stuff that we do, because we almost always want to make causal statements, because that's where the real value in our community is, but we almost never can make it from the kinds of stuff that we do. It's really hard to make causal statements, although there are some places that we will touch on this in this class. So I've been mentioning this phrase, the data generating process, and I want to be a little bit more explicit about that. So the data generating process is some true, in quotes, capital true there, is designed to highlight the fact that this is never a process we see. This is not something we have access to. This is only something we conceptualize and think about. But it's the process and how our data comes to the database that we are going to then try to capture in some form of a statistical model. Put in another way, we have a vision of the world, some empirical vision, and we have data that we want to use to answer questions about that empirical process that we think exists in the world. And then we have some model that we test on the data. This process, this operationalization, the model is the operationalization of this data generating process. So we're trying to operationalize how this larger process comes to be in the form of this data that we then extract in some parsimonious way these parameters for. So a couple of implications in thinking about the world, and we're going to go over an explicit example of data generating processes, and that's going to illustrate another important point that I'm going to make in this class. But just to step back a second, the implications of the idea of a data generating process, I think, are just generally good modeling implications. One, focused questions are better than diffused questions. The more specific and concrete the question, the easier it is to know whether your data can answer that question, and then to develop models that can uncover whatever is going on in that data. So the less complicated the process, the more easy it's to define, the more easy it's to measure, and the more easy it's to understand. Now, that's not to say that our models will not get complicated. Our models will get complicated, and often answering very simple questions involves complicated models. But we can get to that complicated model because we have a very clear sense of the conceptualization of our question. And personally, I think, and this is both from my own personal experience and from reading dissertations and qualifying exams and a whole host of stuff from doctoral students, I think the hardest thing is coming up with a good question. Once you come up with a good question, everything else moves smoothly. But almost never do people come up with the right questions. In fact, most people get to the end of their dissertation and realize that they were asking the wrong question the entire time. And that's good. That's an important lesson to learn, but it's frustrating. So I think that more time needs to be spent trying to understand the question we're asking and formulating a clear question. All right. All models are wrong. All models. The ones you're running are wrong. The ones I run are wrong. The ones you read about that seem so fancy are wrong. All models are wrong, but some are useful. And the way we get to useful models is by seeing where our model fails. So what part of the data generating process is not captured by the data or model? Where is the process that we think is going on, that we care about, that we think produced our data? Where is our data/model not capturing it? Where's measurement failed? Measurement is one of those things that we're not going to spend a whole bunch of time talking about. We'll do a little bit of stuff on measurement. But it's one of the areas that I spend a lot of my time on, and I'm very disheartened in the state of measurement. I feel very uncertain about almost every measure that I use. We always want to understand the uncertainty in our model. And if you're paying attention to politics, and if you're reading sort of the Nate Silver kind of stuff around electoral forecasting, they talk a lot about uncertainty, and they focus a lot on uncertainty because uncertainty is here. It is the currency of our realm, and we almost always want to talk about p-values because we think that somehow that gives us a guard against uncertainty, and that's just a lie. Uncertainty is there, and we really should be more focused on variance than p-values. What we don't know is more important about our models than what we do know. The other thing is your model is not the data generating process, which is unknowable. We're going to use some simulated data in a second, and that's an exception to this. But in general, the data generating process is not something you ever see, but you want to attempt to identify it. You want to really think about it, and you want to be able to have some sense of where your model is failing. What are the blind spots where you can't see things? And I know this is a very general way of talking about it, and I hope that we can be more specific as we move through the semester in places where this is going to occur. But I think the biggest problems are conceptual problems, and so if we want to get to useful models, we need to understand what our model is not doing well, where the gaps in our model are. That tells us where to go to collect better data, or that tells us where we need to add uncertainty to our models. So there's a whole bunch of things that we can do, but only if we know where our model is failing. And we want to interrogate our models like that. All right. So this has been a very general, high-level concept discussion so far, and I personally find those almost useless. Sorry to put you through that. So let's apply this in a very concrete way. So the pandemic has not been great for my weight. I used to walk a lot more. I would walk my kids to school. There's a whole bunch of things that I would do. But in the middle of the pandemic, I'm trapped in my house, in my basement, and recording videos instead of walking around in a classroom. So I'm not getting as much exercise, and I'm binge eating. My wife bought some ice cream sandwiches, which is a personal failing of mine, and so I gobbled them down because I'm just sitting here in my house, bored out of my mind, trapped, distressed by the circumstances outside my door, right? So I've been thinking about weight, and BMI is a great way to measure weight because it has a bunch of benefits. It's a flawed measure, like all measures, for a variety of reasons, but it's where we're going to start. So we're going to think about BMI and what causes a person's weight. We can think of a bunch of things, right? So getting older has not helped my weight. So age is definitely related. Gender is related. Men and women have some different processes, and there's a whole data generating process within the gender component of this. Calorie consumption is obviously part of it, right? Like, so if I'm loading up on high calorie, empty sugar, ice cream sandwiches, that's not going to be as good for my BMI as apples and kale, right? Energy expenditure, how much I'm exercising, that's going to be an important part of it too. Genetics and biology play a role. There's some underlying biological process by which I have some metabolism, and that's all related. Height is built into BMI, but there's a relationship still, even absent that, between height and weight. So there's a whole bunch of things that can affect what somebody's BMI score is. BMI is just weight over height, so it's a height adjusted weight measurement. So let's build a very simple model. We could get as complicated as we want, but let's pretend that we're going to build a very simple data generating process. And we're going to simulate data here. So we're going to know what the data generating process is because we're going to make the data. And there's some usefulness to this, and we'll talk about this in a second. So let's just build a simple model. BMI is a function of age, gender, and then all the other stuff. And all the other stuff are the genetics, calories, all of that other stuff. So we're only capturing a tiny bit of what produces BMI here because we've got age and gender. So I'm going to make this data. Here's the code. Let's switch over to Stata, and you can see the code here. And we can just run this. There's no data. I'm going to clear this. So there's no data here, right? There's an empty data set. There's nothing in my data. So I'm going to create it. So the first thing I'm going to do is set a seed, which is just so that the results are the results that you're going to see here on the screen with Stata running this time are exactly the same ones that you're going to see that I ran last time. So there's nothing about that. I'm going to set 100 observations. So I'm going to say that we're going to have 100 people in our data set. So now we have a data set that has 100 observations, but nothing in it. I'm going to generate an age variable. And all I'm doing here is saying I want ages, I want a uniform distribution of ages. So random numbers are picked between 20 and 49. And so now we just have the ages, right? So I just generated ages, nothing interesting about that. Now I'm going to say that 48% of the population is going to be female, 52% is going to be male, but there's a random process. So they're randomly assigned. So now we have female generated. I'm going to generate a baseline age and then an age squared function, because I'm gonna use that in a second. But the baseline age just sets the meaningful age number at 0. We'll talk about centering in the next lecture quite a bit. What centering enables us to do, when you say control for something in a statistical model, phrases you've used before, when you say controls for something, what you really mean is setting it to 0. And so I want 0 to be a meaningful number. And currently we have no one in our data set that is age 0. And I'm not interested in the weight of somebody that is age 0. So what I'm going to do is I'm going to make 0 20 years old. And that allows me to have a meaningful 0. So now we have that, and then the age squared is because it's going to turn out to be we're going to model that. Now, if you remember from this slide, so we've got age, we've got gender. We're going to do some weird things with age here, but here we have a stochastic process, and by stochastic process I mean a random process. This is a random variable. We'll talk about that a lot more in the next lecture, but suffice it to say, we have a variable here that is the residual term that you have classically used. In this context, it's an error term because it's a theoretical thing rather than a thing that's produced by a model. And the theoretical thing has a mean 0 and some variance. So we need to create that. And so here I've said I've got this random variable with a mean 0 and a variance of 3. And how I came up with 3 is, in order to create these parameters that you're going to see in a second, I actually got some data and modeled it. And so I'm using that as the model, as the underlying, I didn't just make up these numbers, right? So 3 works for me in the context of what I wanted. So now that is random variation around these parameters that we're going to add. So here is our data generating process right here. So BMI is a function of an intercept, which is 26.7. So that's the mean of BMI for a person 20 years old who is a male, period. That's it. 20-year-old male has an expected value of 26.7. For each year above 20, they gain 1.5 BMI points. That function levels off at a certain rate, and that's what this quadratic term here is. So we're allowing a nonlinear relationship between age and weight. And then we're going to say women have a slightly lower BMI, 0.5, and that's probably true. It's a little unclear based on the data, but probably true. So here we go. And we have now created our BMI variable. So we have created, so the data generating process for weight is explicit. It is this intercept plus this coefficient times age minus this coefficient times age minus this coefficient times female plus some random noise. That is explicitly how we've done that. Now, we can capture this in our statistics. So this process you never see, right? Like this model is not what you're going to see in the real world. This is what you're going to try to capture in your statistical model. But here we know what the answers are. We know what we should get when we run the statistical model. All right, so let's run our statistical model. Oh. So we run our data. Let's run our statistical model. And we have 3 variables in our statistical model. We have female, which we know the true answer. Okay, well, so first of all, let's start with the error term. This is the error term that I specified here, 0.3 or 3, and that's 2.8759. So that's really close. So we captured that. Female, I said that female was negative 0.5. We captured that. So although it's a little larger, but it's within the confidence interval here. The age is 1.55, and that's pretty close to 1.55. And then the intercept is 26.7, and here is 27.89. So again, well within the confidence interval. So we've done a pretty good job. You'll notice that the statistical model here is different than the data generating model. The data generating model also included this quadratic term, but I didn't include that in the statistical model, but it still gave me an answer, right? So this is not exactly the same process. This model is not exactly the same one that generated the data. Because you never know the data generating process, you don't know whether you got it wrong or right. Here, you look at this and you'd be like, oh, age is related, female is a little less related than I thought it was, or is not statistically significant. And so you would accept this answer as true when we know it's not exactly the same as the process that generated the data. So thinking about our data in terms of simulation is an important piece. And let me add one element to this. So I think this is important for conceptualization and understanding stochastic processes, and I'm going to strongly encourage you guys to all run data generating processes where you explicitly put that into a model and run a simulation. And you have this code, so you can do this. But the other thing that this allows you to do is what I've done here, which is run a simulation. So you'll notice that there's a few things that I've added here, but here's the model that we did up above. I added some other stuff here for a program, but what the program allows me to do is to do a power analysis. And so if you learn how to do simulation, not only do you get a better sense of stochastic processes, understand what your model is implying, and we'll talk about this as we go through the class, but you also have now a really powerful tool for doing power analysis, because you can generate data for whatever complicated model with whatever data collection structure you're going to use, and you can make a very specific model to test that hypothesis. So here, for example, we can test the hypothesis that that we could test the power for female, and we do that by running this simulation. And we'll have a whole session where we talk about this in detail. But by running the simulation, where I'm running it 1,000 times, I can say with this model, I have a power of 0.15 to detect a statistically significant difference in female. But that's because I only have 100 people. If I were to increase my sample size, say to 1,000, you're going to see that number go way up. And so, right? So now with 1,000 people, I have a power of 0.74 of detecting a difference between men and women at the level, let's see, what did I put here? At negative 0.5. So given this model data generating process, I can estimate what my power is using simulation. So that's something we're going to talk about in this class. But simulating data is a really powerful tool because it forces you to explicitly say what you think your data generating process is, and then you can ask the question, how well is my model doing with respect to that? And we're going to talk about this throughout the semester, but in particular, we'll have a whole session on the end. All right. So that is the end of our discussion of data generating processes. The next lecture is on a review of regression.